Welcome. Thank you for attending today's webinar. My name's Jeff Hancock. I'm going to go into just a brief overview of the agenda that we're going to have here today. Today we're going to have two presenters, myself and Tim Morin from Microchip. Tim's going to go into what is RISC V from a hardware perspective, and why is that really changing the industry in the lakes around there. And then after that, I'll be presenting from a software perspective, challenges and tool chain and runtime considerations. So with that, I'll hand it over to Tim.
Thanks, Jeff. Hi, everyone. My name is Tim Morin. I'm a technical fellow in the marketing department at Microchip, specifically in the FPGA business unit. I'm responsible for defining new products, bringing new products to market. We wear many hats here at Microchip. And before we start talking about RISC V, I really want to talk to you about kind of like current state of the semiconductor industry and maybe even the computer architecture industry. This is a roadmap from ITRS dated 2015. I wouldn't spend too much time looking at the individual rows in the table here. I think the most important fact is that TSMC and Samsung announced a 3-nanometer fab development. And the chip cost is going to be $500 million to $1.5 billion, today's dollars. So it's going to be quite expensive to build a chip in the near future. And in 2016, the ITRS pretty much called it for Moore's Law. It's the end of the road. It doesn't scale like it used to anymore. So they invented some new terminology, more and more than more. And more is literally what it is. It's shrinking, litho down into ever smaller nodes, and you can get an example of how expensive that is. It doesn't happen every 18 months like the original Gordon Moore law. And they also created something called more than Moore's, which is they classify as diversification. It's really integrating analog on the same die potentially, or through something called like a chiplet, which uses 2.5D or 3D packaging, maybe biochips, doing more exotic stuff to still bring the value that the semiconductor industry has brought to all industries, over the last 30, 40 years. So that's kind of like what's going on in semiconductor land. What's happening in computer architecture? Well, over time, there's been great leaps in computer architecture, starting from RISC, which gave you about 22%, on average growth per year. And then we entered the RISC V revolution that gave us significant growth, during the mid 90s. And then we went into Multicore, which gave us a little bit more growth. And then, we got some improvements, in SMP, multiprocessing. But we're, been kind of flatlining for quite a while, putting 8, 10, 20, 30, 40, 50 cores, is just not giving the performance benefits that we enjoyed back in the 80s and the 90s. And an interesting point also is in the kind of like the mid 2000s, Dennard's scaling stopped. Before, with Moore's Law, you also got some power benefits when you scaled. Those are no longer, they don't exist anymore. When you move to a new process, a lot of times you get to choose between maybe a 30% improvement in performance or a 30% improvement in power, but you don't get most, you don't get most of those together anymore. So, Moore's Law is broken, Dennard's scaling is broken, cost and power are increasing, and arguably computer architecture is dominated by two companies, right? So how can RISC V help? Well, what is RISC V? It's an instruction set architecture at its bare minimum, and it's clean slate. All right, so no baggage. It derived from academia, from Berkeley, and they were able to learn over the last 25 years, what is a good instruction and what isn't a good instruction, right? And because they were able to start from scratch, there was no big customer or a particular market segment pulling them in one direction or another. They were able to create something simple. And a 200-page manual versus a 2,500-page manual is a good indicator of simplicity. And also, what architecture would you rather debug if you had to look at and try to find a corner case? I know what I would choose. And it's modular. It was designed to be modular. So very small baseline ISA to form like a basic computer. And extensions, RISC V extensions, add functionality. All right. And because it's clean and it's simple and it's modular and it's small, there's a whole lot of opcode space that's been reserved specifically for customization, not for extensions, but to allow individuals, companies, academia to create their own custom extensions. And we'll get into reasons why that's important moving forward. And it's community designed. It's kind of like open source designed instructions. People come together and talent is harvested across the world, both in academia and in big companies. And so the idea is to grow with extensions. Okay, we're going to classify a group of instructions, put them in an extension, and then we'll ratify the extension. Versus, I want to add another variant of a multiply instruction, so that over the course of 20 years you have 50 different multiply instructions. All right, that's very inefficient. Okay, and there's a foundation that's been set up called the RISC V Foundation, which extends the ISA through extensions, but for technical reasons only. Okay, not necessarily because maybe they have one big customer that asked for an extra instruction. Okay, so it's designed to be small, simple, extensible, lots of customization. So individuals and companies can create custom accelerators. Okay, and there's a foundation that's been set up to protect the ISA. Once the ISA extension has been ratified, it's frozen forever. So what do we have today in terms of standard extensions? RISC V uses lettering to denote an extension. Here we have MAFD, which would arguably, create, what most people would call a basic computer that can do add and subtract, multiplies, divides in both integer and, floating point arithmetic. A for atomic instructions for, bit manipulation. And G is just a kind of a can to collect all the previous ones. Q for quad precision and C for compressed. You can also see that there are effectively 4 base instruction set architectures. 32-bit integer, 32-bit E is a small 16-bit kind of a machine, 64-bit machines, and even 128. 128. Well, why would you design a 128-bit, a machine? It's getting pretty close to, storage companies wanting to, address that 65th, 66th, 67th bit of storage. And I think most people like being able to address things randomly versus using a segmented architecture. And effectively, that's why, our RV128 was created. So it's kind of future-proof for many, many, many years out. Now, some of the instruction set extensions that are being worked on are listed here. Decimal, bit manipulation. Of import is dynamically translated language, J, like for Java. That would be very important for the mobile market. And V, vectors, very important for machine learning, artificial intelligence types applications. Those are well on their way to becoming ratified, and they should be ratified very, very soon. Okay, so we have an instruction set architecture. It's a list of instructions. What does that mean? Well, one of the things is it's free. It's free and open. Anything free and open enables innovation. Nobody's restricted from thinking about creating something new. They can just go off and do it. every company who decides to adopt RISC-V effectively gets an architectural license for free. I don't have to pay somebody money to design my own computer to meet their predefined architecture. I got a clean slate. What this means is that, the golden age of computer architecture starts all over again. That time frame when CISC and RISC were just creating, every year 22, 23, 24, 5%, growth in single program execution speed can happen again. And a lot of that can happen through custom instructions. You make a domain specific computer to tackle very specific problems, and you can design these chips to be put on cost-effective processes. Put them on a 28 nanometer process, for instance, instead of a 3 nanometer process, where your chip development costs are significantly lower, and crank out more chips that solve domain-specific problems. And that's what I just said. So we'll just keep going. Now, the other important thing is because it's clean slate, clean design, security can be built in from the ground up versus patching things. I think we've learned some very interesting lessons in the last few years, Spectre and Meltdown being one of them. Anytime a machine saves state, either in branch prediction or any kind of out of order machine, even a cache, there's a potential for, there's a risk vector for an attack, okay? And the RISC-V Foundation is spooled up a security working group to address this so that the users who develop, future RISC-V chips can have a very robust, secure environment and secure specifications to design around. Now, we at Microchip and the FPGA business unit settled on RISC-V for our next generation product called PolarFire SoC. It's a 5-core RISC-V processor subsystem. Everything you see there in the white with the gray boxes are all hardened. It's not implemented in FPGA gates, and it's coupled to PolarFire FPGA, which is a very low power FPGA fabric. So we deliver 30 to 50% lower power than some competing devices, and saying 10% lower is kind of interesting, but may not move the needle for a customer. But 30 to 50% does, and in a lot of cases, we have customers designing with our products, and they're actually removing fans from their systems. And a fan is kind of it's significant. It always fails, and it costs money. There's no such thing as Moore's law for fans. The cost of fans always goes up because you're buying materials, and they don't shrink. We have the ability to do mixed real-time in Linux, and I'll talk a little bit about that in a second, but we have what's called a very deterministic L2 memory subsystem. The L2 memory subsystem is very versatile. It has what's called a LIM mode, loosely integrated mode, which is deterministic. And we also, because it is RISC-V, we're able to go to our partner and say, hey, we want to achieve determinism, and we'd like you to be able to give us a switch that we can turn the branch predictors off. And so now you can either power up, turn the branch predictors off, or turn them off in the interrupt service routine to enhance determinism. The other thing that we kind of invest in is security. Microchip is the #1 supplier of secure or semiconductors into the DoD space. And so we take our cues about what security means from defense contractors. Microarchitecturally, we chose a 5-stage in-order machine, which is naturally immune to Spectre and Meltdown attacks. Okay. We also have 2 methods to securely boot the processor subsystem, one that we define and provide and open source, and there's another method that you can customize if you have your own unique secure boot needs. The chip also has 128 KB boot flash for you, and it can also boot directly out of that if you don't care about secure boot. Okay. The other thing that's very important is reliability. We're exceptional in this space. I use the word exceptional because volatile memory, SRAMs, DRAMs, are susceptible to neutrons flying around in the atmosphere. And a neutron can impart enough charge on an SRAM cell or a DRAM cell to change the state of it. Bits can flip. And that's kind of a severe problem in an SRAM-based FPGA because these SRAM bits are used to actually provide that configuration and the programmable part of the logic. And if a bit flips, your logic could change, or a routing interconnect can be either disconnected or accidentally connected where it shouldn't be. And we're completely immune to that. Okay, so we talked a little bit about real-time in Linux and a very configurable L2 memory subsystem. We put a very large L2 memory subsystem on this product. It's 28 nanometers and it's got a 2 megabyte L2 cache. That's virtually unheard of. It's a 16-way set associative cache, so each cache way is 128 kbytes. It's got 3 operating modes, as a cache, it's a write-back cache, as a loosely integrated memory, which provides you that determinism, and as a scratchpad memory. We'll talk about the LIM here right now. So when the device powers up, one way is configured as an L2 cache. That means the rest of the ways can be configured as LIM, and they are by default. And the way the LIM works is it's deterministic. It's like an L2 cache hit, so it has that performance, but there's no cache miss. Okay, and the cache is constructed out of 4 banks of memory, and the ways are striped across all banks. So in some architectures, there could be some interaction between the cache, some other CPU doing something else, and the LIM. Well, we prevent that from happening because the LIM gets higher priority over the cache, because the cache is designed to hide latency and improve performance for, say, maybe running Linux on 3 cores, but you want determinism on that 4th core into the LIM memory subsystem, so you want that to have a priority. All right, you're willing to trade off performance on, say, a rich operating system, but you need the determinism for your hard real time, and you simply address the loosely integrated memory at a specific address, and it just looks like an address space. Okay, now if you want to try PolarFire SoC, there's a kit coming out here real soon. It's there's a picture up there on the right hand corner. That's our first prototypes. It's functional, it's up and running. They'll be available very, very soon. I can't announce the date yet, but if you want to be alerted to the availability, just email polarfiresoc@microchip.com, and we'll put you on a list and give you a heads up as to when they're going to be coming available. This is going to be the first product in the market that has RISC V cores from a company like Microchip, a name brand for processors. I'm expecting a lot of demand for this, and I'm really happy to be partnering with Mentor and some of our activities together. And I'll take it over here to Jeff, and he can pick up where I'm leaving off. And thank you very much.
Thanks, Tim. All right, we're going to switch gears here a little bit and now talk about the software perspective with RISC V and some of the things that we need to think about when developing software around the RISC V architecture. As Tim talked about, there's a lot of great unique modes and features and functionalities of RISC V, and actually in particular, he highlighted some of those around the PolarFire SoC out there. So how can we leverage these from a software perspective, right? So he made mention of multiple cores on the PolarFire SoC. These cores are also heterogeneous out there. So what does that mean when I start to develop software for this SoC? Same with safety. How can I really take advantage of the safety and power management functionalities that are being provided? And then obviously from a toolchain perspective, what things from a toolchain perspective can also help me optimize my system here. So let's dive in a little bit deeper on a few of these topics, right? So, Tim mentioned on the PolarFire SoC that they have these heterogeneous cores on here, right? Which is fabulous because now with these heterogeneous cores, it allows us to do a lot more possible consolidation of systems and functions now onto a single SoC. In the past, we maybe had different CPUs that had certain functionality that now we can move those into a consolidated SoC and still provide those functionalities that they have, but now on a single device, which is great because that helps lower our cost, our hardware cost out there. Going beyond that, right, as we start to think about all of these different subsystems that now we're bringing into consolidated in here. Now, in the past, we may have had dedicated devices and systems that were focused on, let's say, functional safety, and some that weren't. And as we're bringing these together, the hardware now allows us to have these mixed functional safety type systems all on the single SoC, because now they're providing these separation capabilities within the hardware to ensure the different subsystems can stay separated. So as we start to think about these heterogeneous multiprocessing type challenges, right, now we need to think about, from a software side of things, a few different things. Utilization. I have all of these different cores that are out there. How can I efficiently utilize all of these compute resources that I have available in the system that I'm architecting out there? Is separation required out there? Getting back to that mixed functional safety capabilities that I just highlighted. How am I going to separate these different types of functions all on this consolidated system? Resource sharing, right? So, there's only so much hardware on this SoC, and so for some things, peripherals and other things, how am I going to resource share across now this consolidated system? So while it gives us this great flexibility, it also kind of ratchets it up that complexity. But that's okay. There's things out there that can help us lessen that complexity and really take advantage of the hardware there from a software architecture perspective. So one of those things that can help us with that is this multi-core framework. So as we start to unpack these heterogeneous cores, right, I may have real-time cores that I am running a real-time embedded operating system on, something like Nucleus. But then I may also have these application cores that are running more of general purpose type operating systems, maybe a Linux or something like that. You could also run some real-time operating systems on top of that. So, we see lots of systems where they might even have a mixture of Linux and Nucleus on there. They may even have a hypervisor or something running on these application cores, right? So you can start to imagine from an architectural standpoint, now I'm leveraging these multi-OSs that are sitting on top of these multi-heterogeneous cores out there as well, which is fabulous, but there starts to become some challenges on there, right? So how do I bring up the system, right? Maybe I don't need to have certain OSs or certain domains brought up right at the very beginning, or maybe I want to bring them down. This helps from a power consumption standpoint, right? Also offload and compute and acceleration type applications out there. So having a lifecycle management component over there is critical. There also could be times where there's boot time requirements, right? Where I have to boot up within a certain fixed amount of time, and the real-time cores or a Nucleus, for example, can boot up very, very fast to be able to meet those requirements while the rest of the system's coming up. So having that lifecycle management is very important for a lot of different reasons. Then obviously, once you have a system up and going, how are all of these different environments going to communicate and play nicely together across all of these heterogeneous type environments, not only just from a hardware perspective, but also from a software perspective over there as well. And so what we've done at Mentor is we've created this multi-core framework that really addresses these type of scenarios, right? The lifecycle management of bringing up, different environments and even taking them down. And then once they're up, how do I, pass communications, interprocessor communications all between these types of environments. So we do that using standard functionalities that we've actually upstreamed into Linux, and so things like remote proc and RP message are common components that are within the Linux runtime. And then obviously from a Nucleus perspective, we've included those as a part of our Multicore Framework edition to be able to give the user now this capability of the lifecycle management as well as the communication once the system's up and going. As we move forward, right, we can even expand even beyond that, right? So as we were talking about on the first slide there around these heterogeneous cores, it now opens up the capability of this mixed safety criticality all on the single SoC. And, hardware is critical to this, right? We need to make sure that we have the appropriate separation out there. There's a safe boot capability. How do we configure, all of the hardware to take advantage of that to, from a hardware perspective to make sure that that safe world stays safe and the non-safe world doesn't, intrude upon that. But why would somebody want to maybe even do this, right? Well, if we start to look at from a cost perspective, right? If you have devices in the past where you have like this mix or this functional safety, there have been times where people needed specific functionality that really, to be honest, didn't need to be certified. They put it in there because they couldn't figure out ways to separate them. Well, now you can with this functionality separate those. And so you can now go and just certify the functions that you need to be certified, and all those things that don't need to be certified, you can put into the non-safe domain. What this does is now it lowers the number of lines of code that you really have to go and certify, and it then in turn then lowers your certification costs to be able to go and certify this device, because you're really only certifying the functions that you really need to, and those non-functions you don't need to. So that being said, we can leverage a lot of the hardware, right? But there are still some things on the software side of things that we need to take into account, right? So like interrupt flooding, for example, the software communication mechanism between that safe world and the non-safe world needs to prevent these type of things. And so what we've done is we've taken our multi-core framework and we've created a certifiable version of it. So our Multicore Framework cert product out there. And its function primarily is focusing on that RP message communications between that safe world and the non-safe world. The lifecycle management, to be honest, because there's the safe boot, or sometimes it's also called a secure boot, capabilities, that's really being taken care of by the hardware, right? Because a lot of times the hardware separation needs to be handled during the boot process and things along those lines. So that's handled by the hardware, which is fabulous, but you still have that software side of things. So with the Multicore Framework cert offering, we can now provide that protection from the software side between that non-safe domain and the safe domain out there as well. All right, some other challenges that we see is, Tim mentioned the great low power performance that the PolarFire SoC is bringing to the market, which is great. But from a software perspective, especially from an application perspective, right? How can I really leverage the hardware capabilities around this power management in an easy to use way, right? I mean, if you look at a lot of application developers out there, they would really prefer to extract the hardware as much as possible, right? And I've even talked to customers where The application developers, they're just writing to a set of APIs. They don't know what hardware is underneath. And to be honest, in some cases, they don't even know what OS is running underneath because they've extracted it so high up. But when you get into power management, right, there's a lot of different optimizations, tweaking that can be here that it can be kind of difficult for people to be able to program at that level to really efficiently take advantage of the power management. Not to mention just the potential of extra code that may not be necessary to be able to go in there. So once again, trying to make life a whole lot easier for the users, what we've done with Nucleus is being able to add this power management framework that really allows the software developers to be able to still take advantage, harness all of that great capability of the power management that the chip offers, but in an easy to use way that the software developers then can manage all of these different capabilities in a way that makes sense to them. So they can now create these different states and that can manage all of these different types of capabilities and use a common high-level simple API call to be able to do that, right? So maybe I have a system that has some or a display, USB, and I don't know, Wi-Fi or something along those lines. And there's a state that just says, you know what, as when we get to a certain state, I want to put those three things into sleep or dim the display out there, right? And so they can create these states and basically say, oh, put this, state number one or my low power state or my you name the state into a sleep mode or into a dim mode or something like that. And they can do that programmatically versus having to go really and get into the bits and bytes. We handle that from the OS perspective with our power management framework here. And so what it does is the output of this, right, is it makes it a whole lot simpler for these application developers to be able to take advantage of this while also minimizing the footprint that's out there as well. So it's a win-win, right? You get the great power management capabilities that the part that can produce, but you're also not increasing your footprint, and also more importantly, your application team can be more efficient because they can then write their code in a way that makes sense from an application perspective. Another area that Tim highlighted is all of the security features that are out there, right? Security itself, let's be honest, there's a lot of things that we could talk about for security, and I wouldn't do it justice talking about it on a single slide here. If you're interested more, Mentor, we do have additional webinars, white papers. We're more than happy to talk about all of the different security things that we can do and things from an architecture perspective you may want to look at and everything like that. But I didn't want to highlight just a few that at a high level, just to make you aware of from a security standpoint we have, right? So one of the big things is vulnerability monitoring out there, right? So, as you get into, things, you're constantly having to monitor the vulnerability. Mentor, we have services that provide that security vulnerability monitoring out there. We can do, we have a security officer that can also look at architecture assessments and everything like that. Obviously, we're embedded devices, so having secure boot enablement out there, encrypted file systems, yeah, those are given out there. But as we start to even get these devices connected out there to different cloud platforms out there, right? Secure device onboarding to those cloud platforms. We provide that, as well as secure remote software updates out there. All of these things can come into play. I mean, heck, if you even look at what I described on the mixed criticality from a functional safety standpoint, a lot of those similar concepts that we talk about from separation could also even apply to security out there as well. So, like I said, security is its own great topic on its own. And if if you want more information on that, please feel free to contact Mentor, and we'll be more than happy to go into a deeper dive on that. Toolchain. So toolchain is one of those topics that some people just kind of take for granted. But if you stop and think about it, right, the toolchain is one of those most important things that you could have on there. We could write the best heterogeneous power management secure software in the world, and if our tool chain's not optimized for the hardware that we're going to be running on, it really falls short, right? It's going to be slow. It could be large in size. Won't even take advantage of some of the hardware capabilities. So, toolchain is at the core foundation, right? Is something that we really need to look at and think about out there, right? And so, if we look at the tool chains out there, there's some great tool chains out there for RISC V, GCC, LLVM, supported by the community. It's great, right? There is a little bit of a downside on there, right? I mean, yeah, you get all of the innovation and things along those lines, but when you start to look at the tool chain specifically, right? Hey, how are things going to be maintained out there? Sure, there's a large community out there, but if there's a specific fix that you're looking for, when's that going to be adopted by the community and fixed out there? Maintenance out there, right? Who's going to do all of the CVE monitoring and all those other things that go into that, right? And then even long term, if your system is is going to be in the market for 20 years, maybe it's an aircraft, maybe it's an industrial control, maybe it's an automotive or something like that have these really long life cycles out there, right? How are you going to maintain all of these things over the entire period of your product out there? And so when you start to look at these things, commercial offerings for these great GCC and LLVM become more and more important out there. And as we start to look at RISC V just in general, right, with the cons as well, one, how fast it's moving, but on top of that, the customization aspect of it, right? From a toolchain perspective, how are you going to be able to leverage some of these new features and functionalities that are getting put into that, or maybe you've created on your own out there. And so being able to customize the tool chain is something that becomes even more important out there for not only just to be able to leverage a lot of the things that are out there with new ISAs and everything like that, but to really optimize your specific system out there as well for the performance, right? So you could do that. You could have your own compiler gurus out there, or you could come to a company like Mentor that's all we've been doing, with our code sorcery team, is compiler optimizations, GCC, LLVM out there. So beyond that, right, you also then, with a commercial offering from Mentor, right, you get the CVE patches, you get the bug fixes. If you're going into that functional safety, right, you can get the functional safety artifacts. And then for those long-term projects, right, we also offer long-term support out there. The great news is for RISC V, we got that available now. So you can go to the link here below, and you can actually get the RISC V SDKs for GCC as well as LLVM out there. Tested, supported on a lot of the popular target supports out there. Because if you start to think about it, when we're looking at tool chains out there, it's really an SDK that's out there, right? So beyond, just your compiler, right? It's got the compiler, it's got the linker. It also has a development environment, a debug, right? So GDB, for example, out there. Be able to support all the really important libraries out there. Obviously, language support is important out there, but then, what targets have been supported, linker files have already been created and everything like that. That complete solution, that complete SDK out there. we have it here. And if you're a GCC guy or an LLVM person, doesn't matter. We got them both for you, which kind of fits into the larger, you know, ecosystem of just Mentor embedded. So, you know, you've heard me throughout the presentation talk about Nucleus. So, you know, what is Nucleus? Well, it's our real-time embedded operating system. It does things that you expect a real-time embedded operating system to do: high performance, high reliability, highly secure, for these connected devices. But to be honest, it's also scalable out there, right? I mean, so if you're going from a 32-bit to 64-bit, it scales out there. It also scales in features and functionality. So if you're into more resource constrained environments, memory or other things like that, that's a strong suit of Nucleus, right? It can get into these resource constrained environments with the features and functionalities that you need, like power management and the likes, but also can scale up from there, you know, with things like SMP and everything. And then obviously we have a certifiable, and actually in Nucleus case, a certified version of Nucleus that can help you when you're going through that functional safety out there as well. Linux, yes, we have our own Linux distributions out there, right? And so we can, you know, provide Linux offerings out there, Linux services out there, especially, you know, when you start to look at services work, customization of a platform, CVE monitoring, all of that good things we have here at Mentor with our Linux offering. The Multicore Framework, I talked a lot about the Multicore Framework in the early part of this presentation, right? And be able to do that lifecycle management with our Multicore Framework, be able to do that communication across these heterogeneous environments out there. And as I mentioned earlier, there's a certifiable version of this as well, that for those mixed safety criticality type applications on a single SoC, be able to enable that functionality out there. And then we didn't talk a little bit too much about this, but I did want to mention this, right, is the IoT framework capability, right? So be able to easily do a lot of that when we were talking about the secure onboarding across the cloud platforms out there. And to be honest, it doesn't, you know, you could switch between different cloud platforms, right? So it gives you that abstraction at the device level of connecting if you're doing an Azure or an AWS or other things out there, a MindSphere, you know, be able to do that. Also, you know, that you know, remote over there updates, you know, with the security and everything like that. That, you know, our IoT framework has that. And these are just some of the highlights, right? I mean, if you look at just Mentor as well, you know, we could graphics, IoT, artificial intelligence, ML. You know, it's one of those things from a tools provider, solutions provider. I didn't even mention the tool chains, right? The code sorcery tool chains out there, right? So if you really step back and look at it, Mentor is one of the few, if the one and only, that can provide the complete comprehensive both runtime and tool chain solution for your needs for RISC V and for even the PolarFire SoC. So as Tim mentioned, the reference board that is coming out later this year, they were nice enough to provide us with some early access to that. We already have Nucleus running on some of the early prototypes of that device out there. So when that PolarFire SoC board comes out, you're going to be able to take advantage of Nucleus running on there. And you know, all of this is backed, you know, with 25 plus years of embedded experience, billions of devices out there, really broad market embedded portfolio out there, the connectivity. So yeah, thank you.